Oh, sorry, I didn't even see you there. Welcome to 61C lecture on how to run a program. Woo! Great to see you. Today we're going to talk about compiling, assembling, and linking and loading, otherwise known as CALL. Note the first three letters of that. Go Bears, folks. Love it. CAL. So let's first do a little review, interpretation versus translation. These are two ways to get a program to be run on a computer. High order, start from the beginning. You've seen this picture before. This is a beautiful layer of abstraction we learned in this course. Everything above the ISA instruction set architecture layer is the software. The stuff below is the hardware. And today we're going to talk about all of it. Everything above the ISA is today's fair game. We're going to talk about how to go from a high-level language, or C, to a assembly language. I wouldn't say middle level, but a lower level language, assembly, to the lowest level machine code, and how to understand what that is. Pretty exciting. So in some context, one way to run a program is interpretation. An interpreter is a program that runs other programs. And so we're going to think of languages that have from a continuum from the left, really easy to program, so much fun to program, to the languages on the right, which is if you had to write this code by yourself without any help from a computer, it'd be really hard to program. But on the right, again, the right is very efficient to interpret, really fast. Just take it and go. Really inefficient to interpret. So you see that the languages on the left are slower, and languages on the right basically are faster. And so this is kind of a sense of that. So here's Python here. Python, the easiest language you can imagine to write in. There's obviously above that, but from what you've seen so far in the lower division, Python, a little bit harder to write in, but a little bit more efficient to interpret is Java, and then C++. All the way continuing to the right, assembly and machine code all the way on the right. Certainly if I said, by the way, this is what people back in the day had to write in, okay? So if you were thinking about early days of the ENIAC, boy, that's what you were working in. So much, much harder. We think of Java bytecode as something that's pretty efficient to interpret, so we appreciate the speed of Java not being a fully interpreted language. You know that Java, you compile it down to this bytecode and then you interpret the bytecode. And that's the part because the interpreter can run on many machines. Great, same as Python. Python basically runs on any machine, love that, as does Scheme. Here's C here, and C is somewhere in the middle. So C is not certainly a high level, we call it a high level language, but it's not as easy to write in and to work with in terms of, it's much faster though, certainly when you compile it down. So let's talk about the other option, what compiling means. So language translation gives us another option other than interpretation. The idea is translation says, take the language from one, translate it to a lower form that's farther to the right on that curve, on that spectrum, and then run it straight. So that's basically what we do in C. We translate it to the lower level machine code. So usually interpret, of a choice, by the way, you could interpret all of them and you could translate all of them. Usually translate to the lowest level on the right. So you move things for a translation to the right in that idea. So you can interpret all of them. You can interpret Java. You can interpret C. People say, oh no, you have to compile C. You can interpret C. People have written C interpreters before. So you could do that as well. You typically interpret high-level language when you don't care about performance, and you typically translate to a lower-level language for increased performance. You can just run it basically straight on raw silicon. So how do you run a program? You have two options. You have an interpreter or a translator. Interpreter directly executes the program in whatever the language it is. Here's Scheme, high-level language, and let's run it right there. Here's Python, run it right there. A translator converts it to a language kind of farther to the right, as I said a second ago. So here we are, interpretation. I've got foo.py. It runs through an interpreter, and it goes. Interpreter is just a program that reads in the program and then performs the functions, and then you see the output. Love it. Why do we interpret machine code in software? So why would you ever interpret machine code? Why would you do that? Well, if you had wanted to simulate something. So in Venus, we have a RISC-V simulator, and you can now take this assembly that normally would be translated down to machine code and then be run directly. You could interpret that and be able to have a lot more debugging information. You could have, it's easier to write, it's kind of nice in the window environment. Also, if you ever convert your ISA to another ISA, back in the day, the Apple moved from 68,000 to PowerPC. This is before they moved to x86 and now before they moved to ARM. If you want to make your system backward compatible, you could say, you know what, here's the new ISA and the hardware. The hardware supports the new ISA, but you have code in the old ISA. What do? Well, you could interpret it. You could pretend, this is like Scheme in a way, and make it work with this. Much slower, it's not running raw anymore, but you can interpret it to backward compatibility, which is great. So we love kind of emulators do that exactly. That's what an emulator does in some sense. An emulator takes low-level code intended to run directly on silicon and pretends you're in software and emulates it, interprets it, and pretends that you're running on that hardware. So from the point of view of the program, here's the beauty of abstraction. Point of view of the program, I don't know whether I'm running on an interpreter or running on raw silicon. It works. When I give it an ad, it does the ad. Now, is it a software thing that's doing that, or is it the hardware doing the ad? From the program's point of view, we don't care, and that's really beautiful. So it's really nice to be able to have backward compatibility if you interpret another instruction set. It's pretty cool. It's also much easier to write an interpreter. So if you have a choice between the two, this is, again, the first series of these lectures is basically just comparing interpretation and translation. Then we'll go to CALL after that. Again, interpreter is closer to the high level, so you can get great error messages. You can get great debugging support. Well, from the translator point of view, if you're in the compiler, assembling, loader point of view, well, you can add extra information. As I'm compiling it down, I can make a note of what line it was and add that to whatever information I'm passing on to the next generation, the next level of that pipeline, to be able to then, if I'm running it, be able to feed that information back. Oh, here's an error. The error is on line 14. Interpreter, you're looking at line 14. Up, error on line 14. You tell the user, line 14 error. But if you're a compiler and then translating it to something the assembler can take and something the linker can take and something the loader can take, it's a little harder. I mean, you have to do some work, but you can encode what line you were looking at it when you first saw the code so that that passes on. And so when you're all done, when you're running the program, it'll say, hey, by the way, there's an error and it was on line 14. Hey, that's pretty cool. I love that. So that's a reaction from the translator community to be able to pass information down the pipeline in some sense. In terms of speed, we've talked about this before. Interpreters are crazy slower, but again, we choose interpreted languages when we don't care about the performance, or when we're interpreting another ISA. We're trying to let backward compatible code. We're trying to take code from another program, run on my program as well. Code's much smaller for interpreters than compilers. You got to think about a lot of things, and there's a lot more work to write a compiler. And in fact, I'll give you a little taste. 164 is a course if you want to learn more about that. The other nice advantage of interpretation is it provides instruction set independence. If I'm running an interpreter in Python, I don't really care. As long as I have a working Python system, I don't really care what hardware I'm running on. Not the same for translation. I translate down to a particular hardware so that I can run as fast as I can on that silicon. So again, translated compiled code is almost always faster. That's great. Therefore, high performance. We love that. The other advantage of a translator is when I give you my Python code, here's a great Python program, run it. I'm giving you the source code. I'm giving you the intellectual property. And the advantage of a kind of a the idea of translation is I take my intellectual property, the C code, and then I make an executable, and then I can distribute the executable to you. And certainly there is decompilation where you can reverse the process and try to figure out what my C was originally, but it's much harder. It's really much harder to do that. So rather than give you all of my code, what you can do is I can translate it down to a working executable, give the executable away, download the executable, run it now. I can download Photoshop, and I don't really know what the raw source code was. That's the mountain of code that built Photoshop. I just have a working program. So it's really hard for me to undo it or figure out what that was to make my own version. So that's great. You can kind of hide the intellectual property from your user base who might be nefarious and try to undo that. I have to give it away if I'm giving Python code away. The other model, certainly you know about the other model called open source, and the open source model says, you know what, let's make our source code open source, and then many eyes can be on the prize. You can contribute. Random people who are bored, who retired, can wake up one day and decide to contribute to my code base and help me find those bugs, and that's wonderful. So there's another perspective of, rather than keeping it all close to the vest, is you give your source code away and you let the open source community help you develop it, which is wonderful. And I'm a big proponent of open source code development. The next series of lectures, we're going to talk about C, A, L, and L. We'll see you there.